All right, y'all. Chapter 1, particular questions from exams. Yeah, Abby? Oh, what year? Spring 20. Okay. Number 3. A? I mean, for the free or number 3? No. No. It says 32A. Okay, which of these statements is true? A conductor has more statement. Ask. I just like why are they? Okay. Uh, so which of these are true? A conductor does numbers, because it's neutral. A conductor will be. That statement is not true. An insulator cannot. So if we have an insulator, in the insulator, even though the charges won't move around in a perfect insulator, that the molecules can become polarized. So I can get molecules within the insulator that realign themselves and become polarized. Just like, well, water. No, water is not a good example, but an insulator can become polarized. Well, no, that's the opposite, right? The conduction electrons can move around more freely, and then charges are evenly distributed on the surface of an insulator. That can be true, but it doesn't have to be true. So, the thing, if it said conductor, conductors, the charges are evenly distributed, but not on an insulator necessarily. Did we say for the third option? Conduction electrons move freely, so that's why they're conduction electrons. All right, is that okay? Okay, so in an insulator, it's saying that the charges can move, like the conduction electrons don't move around. There aren't. So if you imagine, let me draw a sheet. So say this is a sheet of plastic or whatever. Do it. The molecules inside the insulator. So this is a molecule that it can get such that I have negative on, but I'm getting a polarization of the molecules within that insulator. And the actual molecules shift around. So that was a conductor. If it was a conductor, well, if it was a conductor, you would have and positive charges down here. That doesn't have to polarize, that the molecules become polarized. They shift around so that negative on one side, positive on the other. The molecule is a little bit negative on one. Yeah, so a negative charge is brought near to a picture, and so what picture are you talking about? Yeah, I see what you're saying. So if we have, I think, so if we have a conductor that is negatively charged, Those negative charges will be evenly distributed. Okay? Because the charges can move around freely and they experience these coulombic forces, and so they will distribute themselves on that so that they're equally distributed. Definitely further apart, like because that's the way the forces will force them into that charges over here, and it's going to leave an excess of positive charges. A distribution of charge where you have positive on one side and negative on the other. I understand what you're saying, and that picture is not incorrect, but I see why you're confused, because in the one hand, this picture right here is due to this charge on a conducting steel. Then they become evenly distributed. In this case, and it causes this realignment of the charge. But it has a net negative charge. It doesn't have to be negative. No, it could be that this conductor is, but the point is that what distributed on the surface of the conductor. They have to be because every charge feels a force, push themselves away into this even distribution of charge.
So that's because it's neutral.
That's the answer because it's up next to a negative charge, but also because it's neutral. But that's sort of not close to it. These negative charges run away. They feel repulsive forces, leaving positive charges over. Negative charges move away. This positive negative distribution on this because of this charge. Over here, I don't have that, so I do have a net charge. Like acting on it, they just evenly distribute. It's like if all felt repulsive forces for one another, like you just dislike, right? You'd be spread out trying to get as far away as possible from each of you. But then if I come in like, oh, this isn't right, I need to all sit together. I was like, and then y'all all go over here. So this is like, this is what y'all would do if you didn't like one another. But,
So if that was an insulator, how would it?
if it was an insulator, yeah, sure. So if it was an so let's imagine that you have an insulator. Except this exception that we talk about where if I have an insulator, I bring a positive charge, then the individual atoms be aligned. You see the difference on the insulator? That doesn't occur. But the individual atoms can become polarized. That's what I mean when I say that an insulator charges don't move around, but the atoms themselves become polarized. Okay, all right. Um, yeah, the charging device allows you to place. So how do we get 2/3 charge on each sphere? You want to get 2/3. So let's just look. If I charge two spheres with a charge, They all come together. Those thirds Q on each one. Follow what I'm saying? I had two Q on two objects. I bring them all together, and it splits up that 2Q. I want to take them back apart on each one. So A is the right answer. And none of the, so for example, if I sphere 1 with Q, so sphere 1, Q, and then touch sphere 1 to sphere 2, that means that both of them will have Q over 2, right? It splits that into, and touch sphere 2 to sphere 3. So if this will have Q divided by what? 4, right? It'll split that in 2. So then I'll with Q over 2 and 2 of them with Q over 4. This tomorrow though, okay? But still, I like that question. It's a fun. Okay. Number 6. I had a class in this room one time, some years ago, and this culture is much better than it used to be. But somebody went back into that closet and they found a bird skeleton. But Pelcher is much nicer than it used to be. It's still kind of an armpit of campus, but it's still much better than it used to be. Okay, don't tell anybody I said that. Oh wait, we're recording this, aren't we? So Q1 is 10 coulombs. Further, I know that Q1 is positive or negative when, and then Q2 has 1, 2, 3, 4, 5 lines. Q going to be bigger or smaller? Lines. I know one. I get rid of that one, and I get rid of that one, so it has to be this. This one's a little harder because we n, that's Q1, times 1, 2, 3, 4, 5 divided by 3. So that'd be 50 divided by 3, or that's 17. I don't usually have ratios, but in this case, you didn't need to do that ratio to figure out that chart, by the way, on an exam, because it's really without answering the question, just eliminating the other answers. There are different variations of this. There are different variations on this too, so make sure you take a look at those. There are some with 3 charges where you have to find the charge, but you do it the same way. Juliana? Negative, and then this would be positive. So this should say positive. Generally, when I have those sort of mistakes, usually the picture is right. Very well, which is sometimes what y'all do too. You too, or you have a question? Okay. Okay. That was the end on this one. 2023, number 8. Magnitude of the net force on Q2. This one. Yeah. So good sort of. Probably gonna have a question. Basic Coulomb's law problem. 23 last year. The magnitude of the net force. First, draw your vectors. Looks like they're all positive. Aren't they all positive? Let's see if those forces are equal, and if they are, then we can just say the answer is C. Is the answer C? No. Force of 8 coulombs, or 8 times 10 to the minus 4. This is 4 times 10 to the minus 4. So this one is twice as big, and the distance is twice as far away. So they're not going to be equal and opposite, right? Because if it's twice as big and twice as far away, force. Okay, so we can't really say it's 0. In fact, I'll go and take that out. Let's go and just calculate these. The force times 10 to the minus 5 squared. Notice I made this easy so that you can cancel things out. And that leaves me with 18. So that's this force, which is 18 newtons. The other force should be 9 newtons if I did my ratio right. So let's just see what that is. The force on particle 3, that's 9 times 10 to the ninth, negative 5, 8 times 10 to the minus 4, divided by 4 squared. That cancels with that and that. That 2 times 8 cancels the 16, and then I'm left with 9. So 18 to the left, 9 to the right. Force is 9 newtons. Like that. So be sure that you can do that. There's one like that. All right? Magnitude. Oh, the charges, they don't say they're positive. You don't see that? There's numbers on that page? You, if you Okay, let's take a look. So usually that's a few years back, because I started doing that on the free. Just any one, is that one like that? Um, a 2D problem. So I think you know how to calculate the magnitude of the force. That force would be in that direction. Because they're oppositely charged, they're attractive, right? They attract to one another. And so now I want to know over R. I want to know this angle. To find that angle, well, notice I have this triangle. That means that this angle is what value? Oh no, that would be the 45 degrees. This isn't a very good example. Um, but to find that, that would be the opposite. This is the side, opposite over adjacent. Remember SOHCAHTOA? Tangent 45 degrees. All right. And then look down at the options. That would be 45 degrees. That would be the right answer. But we could express that too. If this is 45 degrees, we could also, that's 180 plus 20 plus 45. Okay. Okay, so here I have this is a 3, 4, 5 triangle. I'm looking for, I know that that force is going to be in more difficult because, I draw my coordinate system here, but the easiest angle to find is this angle. And then take the 90 minus that angle. So you got to do a little bit of geometry and trig. To find that angle, I'll call this theta. And the adjacent side is I didn't do that, Tan, I just know it. And then to find this angle, that would be 90 minus 37 or 53 degrees. Let's go look at the options. So one option would be 53, and that would be the answer.
So can I make like a triangle with?
Yeah, you could have made a triangle. You could have made this triangle right here. And this would have been 4. And to find that, you would have said the inverse tan of opposite over adjacent, which is like, how are you measuring the angle? In this one, well, I wanted to know the angle of the force on the 5. But as I said, there are several ways to express. I could have also given an option that would have 7 degrees. That's 360 minus 53. 307 degrees from the positive x-axis, or counterclockwise. Well, I mean, some people do that, but I never measure from. Look at the options. Be careful, though. Look at them carefully. Sydney?
Can you do number 8 like that?
Yeah. Can I erase all this? Because I've sort of messed it up. Is that okay? All right. So to find the force, so I need to know this distance between, that's the square root of 3 squared plus force is going to be k cubed squared divided, sorry, not 5 squared, 10 squared. Sorry about that. 5 times 10 to um, so I get 8 is 10 to the minus 9 newtons, which is B, 1.8 times 10 to the minus 8. 50 over 25. Yeah. All right, what else, y'all? Number 1, the multiple. You'll see them on the exam. You see some problems, they're on every exam, so probably going to see it. Just start by drawing your vectors. I usually start with the smaller. So I have this 2q. Here I have a charge 4q that's twice as far away. Now remember, for Coulomb's law, kqqq over r squared. Charge, or excuse me, I didn't double. Oh yeah, I did. Right. So I want to know, how does the force due to this charge compare to the force due to this charge? This charge is 4 times. Okay? Because if I quadruple one of those charges, which is what I've done, I add a 4 right there. But that's not all I've done. I've also moved it so that it's twice as far away. So if I have a 2 right here, that means I also have a 4 in the denominator. Same as the force due to the plus Q charge. Important. I need to know how big these forces are relative to one another. Otherwise, you're going to get an answer wrong. I draw this one first, and then I realize this charge is 4 times as big as this charge. Normally, that would cause the force to be 4 times as big. However, it is also 4 in the denominator because it's 2 squared. So I get 4 over 4. So this force is equal to this force in magnitude. So then the answer is C because it splits the difference. Now, if, let's say, for example, it's not a problem, but let's say, for example, that this force was like this and this force was like this. Well, that if they're the same, it'll be just down the middle. The bigger force. Example, what would give you that configuration? And then, in fact, boy, that I didn't even draw 4 times as big. It'd be about like that. Then that force would be 4 times as big as the other force. Increase the force by 4. Okay?
No, it was one that asked about potential.
Yeah, if you see that word, I must have made a mistake in my key. So nothing about potential yet.
Can you go to that one?
2018? This one right here? Yeah, I think we did one similar to this. I don't think it was the same one. Um, so if cube B has a negative charge as well, I know that the forces acting on this cube have to be in here because the net force has to be in between those two vectors. And so it has an attractive force for both of those. Since B is negative, that means, well, to be attractive, but notice that if I did it differently, which you'd see other, for example, they had a force like this. And if this one was positive, for example, like you want to first ask yourself where are the component force, and they'll just flank that vector, and then ask what does the other charge those component forces. No fear on faces. Are we okay? Yeah. Okay. That's just like your normal resting face. Fearful. No, y'all don't look afraid. We're okay with that, Juliana? Yeah. They're on a bunch, so let's see. Said it.
She said.
Oh. First thing you want to do, I need to, well, recognize that you know the charge is 1.6 times 10 to the minus 19 coulombs. That's 1 e. And the mass of a proton. That's the fundamental unit of charge. It's it's on your equation or the charge of a proton. So here, the first thing that you would do is to figure. I know that F is equal to Q. That is 1.6 times 10 to the minus 19 per coulomb, and that gives you the electric field. Then I need to know the acceleration. Newton's second law, F equals ma. So A is equal to F over m. So whatever that force is that we found earlier, divided by the mass, 1.67 times 10 to the minus 27. That gives me my acceleration. And the velocity is just the acceleration times time. So there are three steps that you have to go through. Find the force. That's just the definition of the electric field. I think y'all know it. F equals ma. Yes? Yes?
Uh, 18.
Chaos the velocity. Sure. I mean, for your quiz tomorrow, it's whatever's on the past exams. But on the exam, yeah, sure, I could ask you the position. But you remember those equations, V equals AT. Look, y'all try to memorize them, but if you ask me during class, I'll tell you, I'll just write them on the board. But try to just remember them. But if you ask me, I'll write them on the board. Should I just write them on the board anyway? All right, can y'all remind me? I'll do that tomorrow. Okay.
So F equals
Of our electric field. It's on your equation sheet. I think it's written like this. Find the electric field, that it's the force per charge. Electric field is force per charge. Okay? What else, y'all? On this one, yeah. Doug rubs a piece of fur on a hard rubber rod. So I have this fur, and I have a rod, and it leaves a negative charge. That means that the fur, or let's see, fur will be left with a net positive charge. The fur is also charged because it actually gave electrons to the hard rubber rod. Electrons are added to the rod. That's the right answer. You don't remove the material that it is. Like you remove protons, it becomes something different. So you're adding electrons to the rod. What happens? So in a neutral copper wire, that is a conductor, what you're going to get is a distribution of charge that's negative on that end and positive on that end. That 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 copper wire, it's gonna move. The rod. Let's see, the wire will move away from the rod. No, it's going to move towards. Negative charges will move to the right side of the wire. Yeah, that must. What happened? No. Even though I draw it this way, that's not actually what happens. That the protons don't move around. It's really that the electrons leave and they leave a net positive charge. So D is not right, and then E is not right. So B is the right answer. Only negative charges can move, as far as we're concerned. Because I said when you move protons around, you're changing the. All right. Right. Julielle wants it. She's like, yeah, let's put that question on there. Okay. Other questions, Joe?